Welcome to DTH channel, lecture 5 of Atomic and Nuclear Physics. In this lecture, I am going to explain about Zeeman effect, a prominent effect when a spectral line is passed through electric and magnetic field. Prominently, this effect will take place when a spectral line is passed through a magnetic field. Magnetic energy and the energy of the electron interacts there. This effect takes place. This effect is nothing but splitting of spectral lines into more numbers. So, this is one of the advanced effect in atomic and nuclear physics. I am going to present this lecture in the following order: introduction about Zeeman effect, Stark effect, and summary of the discussions that we are going to have. Introduction. Fine splitting of spectral lines is explained by quantum mechanics. Quantum mechanics assumes that energy possessed by a particle is equal to h nu, where h is Planck's constant and nu is the frequency of the wave exhibited by the particle. The wave and particle nature are connected by de Broglie concept of matter waves. In de Broglie concept of matter waves, a fast moving particle will behave like a wave. Energy possessed by the wave is equal to h nu. Then rest mass energy of the particle is mc square. This mc square and h nu are connected by de Broglie. That concept, wave concept, is used in quantum mechanics. Then Schrödinger developed many mathematical equations to solve the physics concepts and to relate the theoretical concepts with experimental results. One of the prominent experimental result is this Zeeman effect, splitting of spectral line when it is passed through a magnetic field. Here an atom is placed in a magnetic field and magnetic energy interacts with the electronic energy. This concept was first looked by Faraday, Faraday's law of electromagnetic induction, Faraday's law of electrolysis. Like that, Faraday play an important role in physics in various fields. Faraday observed this effect by the prediction on the basis of classical theory by Lorentz force. When a particle is moving in the combination of electric and magnetic field, Lorentz force will act on the particle. We would have learnt this concept in our elementary classes. So, Faraday observed this fine splitting of spectral line when it is placed in a magnetic field, predicted on the basis of classical theory by Lorentz and first observed by Zeeman. This Zeeman effect has two forms: normal Zeeman effect and anomalous Zeeman effect. Normal Zeeman effect means splitting of spectral lines into 2 and 3 is normal Zeeman effect. If the spectral line is splitted more than 3, then that effect is called as anomalous Zeeman effect. Quantum mechanical explanation, mathematical equations are given for both this normal Zeeman effect and anomalous Zeeman effect. In normal Zeeman effect, longitudinal effect and transverse effect are there. This longitudinal effect and transverse effects are based on the direction of observation of the observer, the spectral line. This Zeeman effect is the energy shift of atomic state caused by a magnetic field. As we know, interaction between magnetic energy and orbital energy, angular momentum energy gives out the splitting of spectral lines. Here, shifting of atomic states by a magnetic field is also another statement to explain to define the Zeeman effect. This shifting of atomic states is due to the coupling of electron orbital angular momentum in the quantum numbers. This orbital angular momentum is denoted by small l. Orbital angular momentum quantum number is small l. So, this shift is due to the coupling of electron orbital angular momentum to the external magnetic field. Normal Zeeman effect occurs when there is no spin magnetic moment. Anomalous Zeeman effect occurs when the spin of the electron is taken into account. So, normal Zeeman effect is in the absence of spin of the electron. Anomalous Zeeman effect is in the presence of spin of the electron. Now, we will go to the derivation of this interaction energy between the magnetic field and the orbital angular momentum energy of the electron. This interaction energy is given by del E, which is equal to the product of magnetic momentum, orbital magnetic momentum of the electron and the magnetic field. Suppose this B is only in z direction, then that B can be denoted by vector form as B vector is equal to 0, 0, B z, where the x direction component, y direction component and z or 0, z direction alone there is a component. Now, the interaction energy of the atom, interaction energy between the magnetic field and the orbital angular momentum del E is equal to minus mu z into B z, which is equal to mu z into B z m l, where we have seen this m l is the orbital magnetic quantum number, because here this interaction takes place between orbital angular momentum and the magnetic field. So, this m l comes into picture here, which is orbital quantum number, orbital magnetic quantum number, magnetic quantum number. Next, to learn the type of transition happening, we need to use the selection rule. That selection rule comes in spectroscopy. Del mj should be equal to either 0 or plus or minus 1. So, the difference between mj, where mj is the orbital magnetic momentum quantum number, this mj can have values between minus L and plus L. Already we have seen this when we are learning about the quantum numbers. So, considering between transition, Zeeman split atomic levels, allowed transitions will be h nu, that is energy of the emitted radiation is equal to h nu naught plus mu b into B z. So, this is the first allowed transition. For this allowed transition, selection rule is del m is equal to minus 1. Then this del m can have values 0 or plus or minus 1. So, h nu is equal to h nu naught. For this h nu naught, for this selection rule is equal to 0, that is the difference between ml values between should be 0. Then h nu is equal to h nu naught minus mu b magnetic moment into B z. For this, the selection rule is del m l is equal to plus 1. Like that, selection after applying the selection rule, we will see these type of transitions, allowed transitions. This transition has taken place after the interaction between the magnetic field and the electric angular momentum of the electron. Here you could see the pictorial explanation of the Zeeman effect. This is the energy level for L is equal to 2, and this is the energy level for L is equal to 1. We know that for L is equal to 2, the suborbital is d. For L is equal to 1, the suborbital is p. For L is equal to 0, the suborbital is s. Connecting this orbital quantum number and principal quantum number for n is equal to 3, the L values can be 0, 1, 2. So, here L and 2. So, this is P, this is D. So, transition takes place between D and P, sub energy levels D and P. Here you could see only one energy level because there is no magnetic field. Once the magnetic field is applied, this suborbital itself splits into 5 energy levels. So, transition takes place from these 5 energy levels, So, here the first transition is from ML is equal to 0 to ML is equal to 1, ML is equal to 0 to ML is equal to 1. So, here the del ML is nothing but 1 minus 0. So, automatically 1. So, the second transition is between ML is equal to minus here minus 1 2, then ML is equal to 0. So, this is the destination energy level. So, the difference is 0 minus minus 1. So, automatically it becomes plus 1. So, del ML is equal to plus 1. Del ML is equal to plus 1. It is the allowed transition. Allowed transitions are obtained from the selection rules. In selection rule, we have seen that del ML is equal to 0 or plus or minus 1. So, here plus 1 comes, so it is an allowed transition. Then the second transition is, third transition is from ML is equal to minus 2 to ML is equal to minus 1. So, minus 1 minus minus 2. So, minus 1 plus 2. So, automatically for this also del ML is equal to 1. So, selection rule is followed, obeyed. So, this transition is also allowed. So, like that this transition ML is equal to 1 to ML is equal to 1. So, 1 minus 1 0. So, del ML is equal to 0, selection rule is obeyed. Then ML is equal to 0 to ML is equal to 0, 0 minus 0 0. So, selection rule is obeyed. Minus 1 to minus 1, minus 1 minus minus 1. So, minus 1 plus 1 0. So, 2 1, 1 minus 2 minus 1. So, del M is equal to minus 1 is allowed transition. So, all allowed transitions are listed here. So, this is the pictorial explanation of Zeeman effect. Now, coming to the other types of Zeeman effect, as I told earlier, longitudinal Zeeman effect and transverse Zeeman effect. Longitudinal Zeeman effect takes place when the observation is along the magnetic field. That means, if you are observing the spectral line in the direction of the magnetic field, then the spectral line photons of the spectral lines must propagate in Z direction. That is longitudinal Zeeman effect. We know light waves are transverse in nature. So, only X and Y polarizations are possible. So, the Z component del ML is equal to 0 is therefore absent, and we observe only del ML is equal to plus or minus 1. So, the termed sigma component are circularly polarized. So, in the longitudinal Zeeman effect, selection rule del ML is equal to plus or minus 1 is obeyed. So, we got the longitudinal Zeeman effect. Transverse this del ml is equal to 0 is absent. So, if you apply this to this spectral line, del ml is equal to 0 is absent. Del ml is equal to 0 is absent means the 0 to 0 is not allowed. So, this line will not be there in longitudinal Zeeman effect. Like that here -1 to -1. So, this is also not allowed. Then here +1 to +1. So, the center part will not be there in longitudinal Zeeman effect. Here del ml is equal to 1. So, this transitions will be allowed. Like that, this transition is also allowed in longitudinal Zeeman effect. This is not allowed. Coming to the transverse Zeeman effect, when we observe the spectral line at right angles to the field, all three lines are present, that is del ml is equal to 0 or linearly polarized parallel to the field direction, del ml is equal to plus or minus 1 transition are linearly polarized at right angles to the field. So, if you apply this to the Zeeman effect diagram, all the three will be present in transverse Zeeman effect. Transverse Zeeman effect takes place when the observation is at right angle to the field direction. Coming to the pictorial explanation of the longitudinal Zeeman effect and transverse Zeeman effect, this is the direction of incident light, then this is the direction of the magnetic field. That means the incident spectral line direction and magnetic field direction are same. Then you got the absorbing atomic polarization sigma, then the observed absorption spectrum will be of this form, observed spectrum will be of this form. Then transverse Zeeman effect. In transverse Zeeman effect, the incident light will be in this direction, then magnetic field is in this direction. So, the polarization will be a perpendicular one, sigma p and sigma l. So, this is the waveform. So, this is the pictorial explanation of longitudinal Zeeman effect and transverse Zeeman effect. Like that, normal Zeeman effect can be explained both spectroscopically and mathematically. Coming to the anomalous Zeeman effect, anomalous Zeeman effect. This effect was discovered by Thomas Preston in Dublin in 1897. This anomalous Zeeman effect occurs in atoms with non-zero spin. That means when an atom possesses spin, anomalous Zeeman effect is possible. Then atoms with odd number of electrons will exhibit this anomalous Zeeman effect. This anomalous Zeeman interaction energy between the magnetic field and the spin quantum number and orbital quantum number can give a clear picture about this anomalous Zeeman effect. We will go into the derivation of this anomalous Zeeman effect interaction energy. In this anomalous Zeeman effect, LS coupling takes place, where L is the total angular momentum quantum number, and this is z direction in the field. Then this is the total angular momentum of an electron. Then this is the spin of an electron. Summing of these two will give the J. Summing of these two will give the J. This is the total angular momentum of the electron will be the sum of angular momentum of the electron plus spin of the electron. This total angular momentum presages about the external magnetic field at a Lamer frequency. This will presage about the external magnetic field at Larmor frequency. Now, the interaction energy of the atom is equal to sum of interaction of the spin and orbital magnetic moment with the magnetic field. So, the interaction energy del E is equal to minus mu z, this is magnetic moment of the electron, this is the external magnetic field. This magnetic moment is the sum of orbital magnetic moment and spin magnetic moment. So, it can be rewritten as mu z orbital plus mu z spin. That is the difference between the normal Zeeman effect and anomalous Zeeman effect. Now, rewriting this equation in terms of L and S, this equation can be written as L Z, that is angular momentum vector in the z direction plus Gs, which is Landau factor. We will get the expression for this Landau factor later. S is at expectation value of this into the mu b by h cross into b. So, this is the interaction energy of interaction energy between the electron and the external magnetic field. Here, by setting the spin as 0, S z is equal to 0 and L z is equal to m L h cross, where ml is the orbital magnetic quantum number, we will get the normal Zeeman effect. So, under this condition you will get normal Zeeman effect. If we include the spin and orbital magnetic quantum number, we will get anomalous Zeeman effect. So, in case of precising about magnetic field, this S z or L z, neither this S z nor this L z are not constant for anomalous Zeeman effect. Anomalous Zeeman effect. Now, to get the derivation, we must project this L and S onto the z axis. So, L, that is angular momentum, total angular momentum quantum number and total spin quantum number onto the z axis. To project the total angular momentum quantum number and total spin quantum number onto the z axis, you will get the magnetic moment of the electron as expectation value of the magnitude of L into cos theta 1 j vector by the magnitude of the j vector plus 2 into S magnitude of the spin quantum number, total spin quantum number cos theta 2 into j vector by the magnitude of j vector. This is the expectation value. This expectation value times the mu b by h cross. This is the total magnetic moment of an electron when this L and S are projected onto the z axis. Now, I will draw the projection of L and S on the z axis. Let us keep this as z direction and this as L, that is orbital angular momentum quantum number, total orbital angular momentum quantum number, then total spin quantum number. Here this is total spin quantum number, then resultant of sum of these two, vector addition is taking place here, will be j. So, this is j vector. So, J is equal to L plus S, L vector plus S vector is pictorially given here. Here this is the angle theta 1 and here is the angle theta 2. So, this theta 1 and theta 2 are given in this total angular magnetic momentum, total magnetic momentum. Now, this theta 1 and theta 2 can be calculated from the scalar product of respective vectors. The scalar product of respective vectors is nothing but L vector dot J vector is equal to magnitude of L vector into magnitude of J vector into cos theta 1. Then S vector dot J vector is equal to magnitude of S vector into magnitude of J vector cos theta 2. So, from this you can calculate the values of this theta 1 and theta 2, which implies that magnetic moment of an electron is the expectation value of L vector dot J vector by magnitude of J square plus 2 into S vector dot J vector by magnitude of J square expectation value times the magnetic moment by H cross into J vector. Now, using that vector manipulation rule, now using the vector manipulation rule, S vector is equal to L vector minus J vector implies that S dot S is equal to J vector minus L vector in dot J vector minus L vector. This is in the form of A minus B into A minus B. So, if you rewrite this in this form, J vector dot J vector plus L vector dot L vector, L vector dot L vector minus 2 L vector dot J vector. So, expanding we will get this. Therefore, L vector dot J vector is equal to J vector dot J vector plus L vector dot L vector minus S vector dot S vector by 2. So, this is how you can get the value for L vector dot J vector. So, that we get the value of L vector dot J vector by the magnitude of J square expectation value. If a symbol comes like this, it denotes the expectation value of in quantum mechanics, that is the case, is J into J plus 1 plus L into L plus 1 minus S into S plus 1 into H cross square by 2 by J into J plus 1 into H cross square. This is the expectation value of L vector dot J vector by the magnitude of J square. We can simplify that further as, which is equal to J vector into J plus 1, where J denotes the total angular momentum, into L plus 1, where L denotes the orbital quantum number or azimuthal quantum number, and S into S plus 1, S denotes the spin quantum number, divided by 2 J into J plus 1. This is how the previous equation of expectation value of L dot J by J dot by magnitude of J square can be written. Similarly, we can write that S vector dot J vector as J dot J plus S dot S minus L dot L by 2. So, the expectation value of this S dot J, S vector dot J vector by the magnitude of J square, expectation value of this one gives J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So, this is the expectation value of S dot J by magnitude of J square. In the previous case, we got the expectation value of L dot J by magnitude of J square. Now, using these two, we can get the magnetic moment. Why we are doing all these things is to include the spin component and the magnetic component in the calculation of interaction energy. This is the magnetic momentum. So, magnetic moment is equal to minus of J into J plus 1 plus L into L plus 1 minus S into S plus 1 by 2J into J plus 1 minus 2 into J into J plus 1 plus S into S plus 1 minus L into L plus 1 by 2J into J plus 1. So, I will close the bracket. So, this whole term into mu B by H cross into J. This is the magnetic moment after including the total angular momentum, orbital angular momentum and the spin component of electron. This can be rewritten in the form mu is equal to minus Gj is equal minus Gj times mu B by H cross into J. So, here this mu B by H cross into J comes as it is. Instead of this whole term, I have taken Gj, where this Gj is called the Landy factor. This Gj is the Landy factor. Gj is the Landy factor. So, Gj is equal to 1 plus J into J plus 1 plus S into S plus 1 minus L into L plus 1 divided by 2J into J plus 1. So, this implies mu B, mu Z is equal to minus Gj into mu B mj. So, the interaction energy del E between the magnetic field and the electron is minus mu Z B Z, which is equal to Gj, that is Landy factor, into the magnetic moment mu B, B Z magnetic field in the Z direction, and mj total angular momentum of the total component. So, this is how we can derive the Landy factor, including all the magnetic moment and spin moment, all things. So, this is the pictorial explanation of anomalous Zeeman spectra. Here you could find two things. One is the D line, splitting of D line and splitting of D2 line in sodium spectra. This is the selection rule. Selection rule for del J is equal to 0 plus or minus 1, and selection rule for mj is 0 or plus or minus 1. Polarization of the transition follows the same pattern as for normal Zeeman effect. So this is the spectral explanation of anomalous Zeeman effect. The next effect is Stark effect. This is the splitting of atomic spectral lines when it is placed in the electric field. As the splitting of line of the helium spectrum shows, the splitting is not symmetric like that of Zeeman effect. The splitting of energy level by an electric field requires that field polarizes the atom and then interacts with the resulting electric dipole moment. So we got the Stark effect. So in this lecture we have learnt about the Zeeman effect, normal Zeeman effect and anomalous Zeeman effect, interaction energy between the magnetic field and the other components of an electron like spin component, magnetic moment, orbital angular moment. All these things we learned in this lecture. Then in normal Zeeman effect, longitudinal Zeeman effect and transverse Zeeman effects are there. Then Stark effect is a splitting of spectral lines when the spectral line is passed through an electric field. These are the concepts we learned from this lecture. You can learn more things about this Zeeman effect by referring to these books and websites. Thank you.